Hello and welcome to this course. I'm Dr. Sriram Kumar. Today we are going to learn biomaterials and their applications. So now let's start with the use of the biomaterials in our body. So when we think about the biomaterials in our body, so that can be used from head to the toes. For example, if you want to change the color of your eyes, you can change the different biomaterials, and based on that, we can change the shades of your eyes, maybe the green, blue, or maybe the other shades. Even though biomaterials can be used in the ear, maybe the biomaterials can be also used in the dental implant. And this kind of the materials has the application in the cardiovascular disease, maybe the artificial heart there, maybe we have this prosthetic joints, maybe the spinals, if we have this problem in this blood vessel, we can also use that uh, biomaterials as a blood vessel. We can also use the tendon or the ligament kind of the things as the biomaterials. Maybe we can use the biomaterials for this bone fixation kind of things. So these are the key application of biomaterials in our body. So now let's understand what are biomaterials. So biomaterials is defined as the kind of the engineering materials that interact with these biological systems. So that interaction of that materials with the biological systems can be either two types, maybe the therapeutics or maybe the diagnostics. So in the therapeutics, maybe you use that biomaterials for the treatment of the particular disease. So that is kind of the therapeutic application. Or maybe the second is kind of the diagnostic application where you use that biomaterial to diagnose the particular disease, or maybe based on the particular marker. So this is kind of the diagnostic, that means the testing of particular disease, or maybe the diagnose diagnose that particular problem in our body. So we now understand that okay, biomaterials are the kind of engineering material. So we customize that material, and that material used for those medical purposes. So when we think about the biomaterials, so biomaterials will have at least four key parameters. First parameter is about this physicality requirement. So when you think about this biomaterials for use of maybe the dental implant, maybe the bone, maybe the kind of the drug delivery. So for that, we will have the different requirement in terms of this physical state or maybe the mechanical properties of the materials. Maybe we sometimes we need the very hard material, stiff material, and maybe we need flexible material. For example, we need flexible material if you want to have the some flexible material and contact lens in our eyes. If you and if you want to know and replace the material for the bone or maybe dental implants. So for that, we need really hard materials. So it depends on the kind of the application. We need use this kind of the things. And the second key point is about this chemical requirement. So the first and important requirement is that biomaterial should not react with tissue in our body. Otherwise, that will react and maybe that damage maybe the tissue or maybe this biomaterials. And the second key point is that there should not be toxic to our body. So these are the requirements of that material. So we have the physical requirement and we have the chemical requirement. And there is the third kind of the requirement, that is the biofunctionality. Biofunctionality means that if we use that biomaterial, so we need to know whether that material has specific function to that particular things. So based on that specific function, that material, we understand whether there has a specific physical or maybe the mechanical properties of that material. So we, in the terms of these two parameters, we determine whether that material has the biofunctionality. And the four important key point is this biocompatibility. So based on this, we need to understand it before use that biomaterial in the biological system, whether that material is as compatible. In the terms of that, that shouldn't be toxic to the tissue, I mean the organ, and the should, and in other terms, we can say is that that material should be safe in the biological organism. So this is about the key requirement of the biomaterials for therapeutic and the diagnostic applications. Now let's understand what kind of the biomaterials we can use. So based on the requirement, we can use different kinds of the biomaterials. Maybe we have some biomaterials based on this metal. Maybe we have the biomaterials based on this ceramics, right? So for example, in dental implant, we need this metal-based um, um, kind of the maybe titanium based or zirconium based. Maybe we have the dental implants where we need the ceramics kind of the material, maybe titanium oxide, zirconium oxide kind of those materials. Maybe we need this composite materials, and maybe we need this polymer materials. So polymer materials can be used in this drug delivery kind of the things. Maybe the skin cartilage or maybe ocular implant. And composite material we can use either in this biosensor or maybe the implant as well as microelectrodes. So based on the requirement of the material, we can use either metals, ceramics, composite, and this polymer materials. So here, based on their physical requirement in terms of the Young's modulus, stress and strain, and then in terms of the flexibility, we can use these materials or maybe in the combination of these materials. So now let's understand what are the physical parameters. So before that, we understand what is market size and what is the future of the biomaterials. So based on the precedence research, they have reported that the market size of the biomaterial in 2024 was close to $171.35 billion market. And that is expected to increase in 10 years by 2034. That will increase to $523.75 billion market. So there was almost three-fold increase of that market size of biomaterials in the 10 years. So if you are looking for a job, or maybe if you are looking for a career in the biomaterials, so you have the bright future in these areas based on that data. So when you think about the market size, so that biomaterials market maybe types based on the types of this material we use, maybe the metallics, ceramics, polymers, and then biomaterials. And we have the different classification that is based on the application. Maybe the biomaterials can be used predominantly in this cardiovascular disease, maybe the orthopedic, maybe the dental, plastic surgery, maybe the wound healing, neurology, tissue engineering, and ophthalmology kind of the things. So this is kind of the terminology used for the eye disease or maybe the eye disorders. So then doctors use the materials for this used for the treatment of this kind of the diseases. So these are all about this market size of the biomaterials in next 10 years. So whenever we want to develop the product, and if you're looking the career in this that biomaterials, we should know what are the key steps in the development of this product. So for that, if you want to develop the product based on maybe this polymer or maybe this metal kind of materials. So if suppose if you want to use for the polymer or maybe the composite materials, so for that we need to have the kind of the copolymerization process. and we have the kind of the composite materials. So this is the base material, and then we have the kind of this polymerization happens here. And once we get the product there, then we should modify the surface of that base material to make that is biocompatible kind of things. And once we have the biocompatible materials, then we can use in vitro conditions for the testing purpose. And once we get the succeeded in this in vitro condition, then we should test that material in the in vivo condition. And once if we get this positive data response, then we can go for this product shape formations, maybe the initial product design kind of things. And once we have that product, then we should test in on this animal model, and then develop the electronics. Then we need to test on human, and then after we should the marketing and launch products in the market. So these are the key steps while developing this biomaterials. So we need some kind of techniques for the development of the biomaterials. Maybe, for example, we need chemical characterization techniques. For example, we need FTIR, maybe we need SPLC, high performance liquid chromatography, GC, FID. So these are the chemical methods on which we can quantify, and we need the physical or mechanical methods. For example, we need to determine what is the modulus. Then we use the tensile strength, maybe the specific gravity. We use the dorometer hardness. Maybe we need the permeation chromatography, viscosity, SEM, XRD, maybe X-ray diffraction. Maybe we need DSC, differential scanning, calorimetry. So these are the physical methods we need to characterize the materials. And for this biocompatibility test, we need to run this kind of the test where we need to know what is the cytotoxicity of the materials, what is the sensitization or the allergicity, maybe what are the kind of the whether that material can be injected intravenous or maybe intraperitoneal injections kind of things. So these are the things we need to understand. What are the genotoxicity of the materials? So these are the things we need to understand if we want to develop this product or maybe the biomaterials for the drug development. Now, if you want to test the biomaterials, so first we should go for physical and the mechanical testing. And if we get succeeded in that physical and mechanical testing, then we should move to the biological method. So in biological method, we need to test first in vitro conditions, and then in vivo condition. Then we need to understand what's the functional assessment and maybe the clinical assessment. And once we get succeeded, then we should launch product. So these are the key things of biomaterials. So now let's understand the physical and the mechanical properties first. So I put this slide just for the recall. What is the nature of the stress and the strain? Suppose you have the kind of the materials and you apply the external force and pressure on this material. So based on the directional force, this material. So suppose you would just apply the stress on this material tensile stress. So what happens there? Maybe the kind of the elongations process happens. So here, at initial condition from here to there. So from here to there, what happens is you are increasing the stress on the material. So there is tiny change in the elongations. So we can say is from here to this position. So this area is kind of called as the elastic region, because when you will just release the pressure or maybe the stress on this material, so that materials will come to this original mean positions, and therefore you can elongate and then it will come to this mean position or the original position, and that is called elastic elastic kind of this behavior in this particular region. But when you apply the further stress there, what happens is that there is the kind of the here, there's a here change, change in the shape of the materials permanently. So up to this one, what happens with this kind of the things is because of the change in the shape of the material, and this is called the maybe this there is the plastic deformation kind of things here. Plastic deformation. So we get the plastic deformation at that particular point, and then after there is the permanent change in that shape and size of this material. So what happens is, and if you further increase and increase the stress on the material, what happens? So up to this point, what happens? That material will get down. And at particular point, we can say here, so difference from here and to there is called kind of the plastic region. And that is tiny area from here is called this elastic region. So we have a kind of this two kinds of the deformation. One is the elastic, maybe and the plastic deformation. So if you want to develop kind of the biomaterials, so we need the kind of elastic kind of the things here, so that they will break down this material. So we can control the mechanical properties based on these two parameters. So if you just recall what is Hooke's law and how we'll define the stress and strain. So here stress is defined as the force per unit area on this particular area. And here strain is defined as the change. Suppose this is your biomaterial, and if you just apply the tensile stress on this material, what happens? So here, this delta is kind of the things is the change, the increase in the length of this biomaterial. So suppose you have this size of your material, and if you apply the stress, what happens if you just get this one? So this is kind of the increase in the length of this length of the material. This is called the L, and L is the total length of this biomaterial. So based on that, we will calculate what is the stress, and that stress is equal to E into epsilon, and where is the Young's modulus. So from here, we will calculate what is the Young's modulus. So that is this one. So if we plot between the stress and the strain, we will get kind of the curve for the different kind of materials. So here we have three kinds of the material. One is aluminum, one is steel, and the third is the ceramics kind of the materials. So now let's understand. So for the aluminum, so up to this region, so this aluminum behaves as the elastic in nature, because up to here, if you just remove or release the stress on this material, what happens that the aluminum comes to their original position. However, when you apply the further stress uh, uh, more than this one, what happens? There is kind of the deformations happens. So this is kind of the plastic deformations. For the steel, if you just compare this one, what happens here is, so as compared to aluminum, the plastic, so that steel has higher stress withholding. And after this stress, what happens? There is the kind of the plastic deformation happens, and up to here, there is the finally breakdown of that steel. So here we can say, so as compared to this one, we have the more slope here, and here based on this equation, or maybe this equation, we can know the slope of Young modulus by measuring the slope. So here, this slope is better, higher than this one. That means the steel has highest modulus as compared to the aluminum. Similarly, if you compare the ceramics with the steel, so this ceramics has the highest slope as compared to the steel, so that the ceramics has even the highest Young's modulus. So what happening here is, so up to very high stress on the ceramics material, this behaves as an elastic in nature. And if you want to develop biomaterials that needs really high Young's modulus and stress, in that case we can go for the ceramics kind of the materials. And if you want kind of those elastic, maybe we need the less mechanical strength from the material, then we can go for the aluminum kind of the material. So based on the application, we can choose either the ceramics kind of materials, maybe steel, or maybe the aluminum. Suppose if you want to develop dental implant, or maybe if you are developing bone replacement. So in that case, we need very high stress EX modulus kinds of the materials. So for this, we should go for the ceramics kind of the material. So for this one, we should go for ceramics kind of the materials. But if you want to develop maybe for the drug delivery. So for that, we need kind of the very flexible kind of the materials so that can be easily modified in the body conditions. So for that, we need to have the different kind of materials, maybe the polymeric kind of the materials. So these are the things we need to understand. And we have another important parameters based on this relationship is that is the elastic modulus. So that elastic modulus, that is the, as I explained you, that is equal to sigma by epsilon, and based on this one we can calculate what is the Young's modulus. So if you want to develop the biomaterials for the bone replacement, so we need to have that modulus compared to the bone. And the second kind of the parameter is the hardness. So that hardness should be, the hardness of the biomaterial should be the equal to the hardness of the bone. Otherwise, what happens if the biomaterials are more hard as compared harder than bone? What happens? That will penetrate and break that bone in our body. So we don't need we don't want these kind of the things, complications. And the third point is the fractures strength of facts. As the maximum strength that can induce before the fractures occurs. So then that fracture strength we can define based on this point here, this point. So up to here, this material can sustain and after that, then this will take down. So these are the fracture strength. And we have the fracture toughness, that is crack propagation in ceramics. It helps to evaluate the survivability, performance, and long-term clinical success of the biomaterials. So till now, we understand what is biomaterials. And if you want to develop the biomaterials, we need certain parameters, certain requirement, that is in terms of the physical state, physical requirement in terms of the mechanical properties of the materials. And we understand the chemical properties of the materials, then biocompatibility and the biofunctionality of the materials. We understand what is market size of these biomaterials, and we also understand what are the steps for the development of this biomaterials. So tomorrow, next class, we will learn the silica-based biomaterials, and we take the example of the silica-based biomaterials and learn in details why silica-based biomaterials have advantages as compared to the other materials and what are the key application of the silica-based biomaterials. Thank you. Thank you very much. See you in the next class.